At this point in the module, I've already introduced you to the idea of impulse. Here's the idea. Let's say I have a mass moving along with velocity v initial. Then a force comes in and acts on the mass for a time delta t. After the force has acted, the mass has a new velocity, v final. We say that the impulse delivered to the mass by the force, we call it J, is equal to the force that was applied multiplied by the time for which the force was acting. We saw in the previous video that the impulse is equal to the mass of the object times the change in its velocity. We have also seen that when two objects collide, they deliver impulses to each other. So here I have mass 1 and mass 2. The impulse that 2 gives to 1 is called J2 on 1. The impulse that 1 gives to 2 is called J1 on 2. And we saw in an earlier video that those two impulses are exactly opposite, or in other words, we can say that the impulse 1 gives to 2 is minus the impulse that 2 gives to 1. We're going to use this result now to do an example problem. Here I have two masses traveling in opposite directions. You can see that I have already drawn in a coordinate axis. So this is the x-axis pointing to the right. I have mass 1 moving to the right with initial velocity, v1 initial. I have mass 2 moving to the left with initial velocity, v2 initial. The masses are given. Mass 1 is 2 kilograms, mass 2 is 4 kilograms, and then the initial velocities are for mass 1, 5 meters per second, and for mass 2, minus 3 meters per second, and that is negative because mass 2 is moving in the minus x direction. Now we are told that the masses are going to collide, and when the masses collide, mass 1 will exert a 1,500 Newton force on mass 2 for 0.09 seconds. So we want to calculate the impulses that the masses give to each other, and then also the final velocities. Before we go to the solution, let's draw a figure so we can keep track of everything that's going on here. So here is our initial situation over here. In the next figure over here, let's illustrate the collision. So I have mass 1 and mass 2 colliding with each other. And let's draw in a BAM so that we know they're colliding. During the collision, the masses are exerting forces on each other. So let's say that mass 2 exerts a force on mass 1. We'll call that force 2 on 1. Let's draw in the force that 1 exerts on 2. Let's call that force F1 on 2. Notice in the figure here that I dropped the little arrow symbols on top of the forces. The reason for that is that everything here is happening in one dimension, and because everything's happening in one dimension, we can keep track of direction just by allowing these forces to be positive or negative real numbers. Okay, let's also add to the figure that the collision lasts for a time delta t, and I'm going to put off to the side here F1 on 2 is equal to 1,500 newtons. That was given. I'm going to put delta t equals 0.09 seconds. That was given. So that's the collision. Now let's draw in the final situation where the masses have their final velocities. So here's mass 1 after the collision. Here's mass 2 after the collision. Now, we don't know which way the masses are going yet, so I'm not going to draw in the directions of the velocities. We don't know that. So I'm just going to put here V1 final equals question mark, and here V2 final equals question mark. So now that we've done the setup, let's go to the calculation. So for part A, we want to start by calculating the impulse that mass 1 gives to mass 2. Using the definition of impulse, I'm going to say that the impulse 1 gives to 2 is equal to the force that 1 exerts on 2 multiplied by the time interval for which the force is acting. Now we know both of these quantities over here on the right side of the equation, so let's substitute. So F1 on 2 is 1,500 newtons. The time interval is 0.09 seconds. Multiplying together, I get 13.5, and then the unit is Newton seconds. So this would be the impulse that mass 1 gives to mass 2. We also want to get the impulse that 2 gives to 1. Now here we can use the result from the previous video. We have that impulse 2 on 1 equals minus impulse 1 on 2. Impulse 1 on 2 is 13.5 newtons per second, so minus that would be minus 13.5 newton seconds. Now let's go to the second part of the problem where we're going to find the final velocities of the two masses. For this part of the problem, we're going to go to this equation here, which relates the impulse received by the mass to the change in its velocity. So I'm going to just take this equation and copy it up here. To proceed with this, let's just decide that we're going to apply this equation to mass 1. So if I'm applying this equation to mass 1, I would say that the impulse received by mass 1, or in other words, the impulse that 2 gives to mass 1, is equal to mass 1 times the change in the velocity of mass 1. Continuing then, I have that the impulse 2 gives to 1 equals mass 1. The change in the velocity of 1 would be velocity 1 final minus velocity 1 initial. And if you look at what we have here, everything is known except for V1 final, so I'll just solve for it. So I have then impulse 2 on 1 over M1 equals V1 final minus V1 initial. So then I'm going to take V1 initial, move it to the left, and flip sides, giving me V1 final equals J2 on 1 over M1 plus V1 initial. And now substituting, I have J2 on 1 is minus 13.5 Newton seconds. Mass 1 is 2 kilograms. V1 initial is 5 meters per second. Now, before writing out the numerical value, let's do a quick unit check to make sure all of this turns into meters per second as we would expect. Okay, so in this first term on the right, we have Newton seconds over kilogram. Let's expand Newton out into kilogram times meters per second squared. That is times seconds and over kilograms. Okay, kilograms cancels kilograms. We have seconds over seconds squared, so the whole thing turns into meters per second. This confirms that the first term on the right, as well as the second term, both have units of meters per second. So then we can write down our numerical value, which turns out to be minus 1.75, and the unit is meters per second. So that's the first part of our answer to part B. The one thing we have to do still is to find V2 final, and we can find V2 final pretty much the same way we found V1 final. We can start by writing down impulse equals mass times delta V, except this time we're going to apply this equation to mass 2. So we can say then that the impulse received by mass 2, or in other words, the impulse that 1 gives to 2, is equal to mass 2 times the change in the velocity of mass 2. Then we expand out change in velocity 2. That would be V2 final minus V1 final. Here I'm going to skip the algebra steps, but it's very much like what we did over here. And we get V2 final equals V2 initial plus impulse 1 on 2 divided by mass 2. Making the substitutions, we were given V2 initial is minus 3 meters per second. Then we're going to add impulse 1 on 2. Impulse 1 on 2 was 13.5 Newton seconds. Mass 2, 4 kilograms. Here I'm going to skip the unit checking as we did before, but when I make these substitutions, I get V2 final is equal to 0.375 meters per second. So now we have done an example problem using this very important result that during a collision, masses deliver impulses to each other, which are equally strong and opposite in direction. In the next video, we're going to see how everything we've been studying so far regarding impulse leads us to a very fundamental quantity in physics known as the momentum.